In this video, we are going to take a look at section 6.4 on the central limit theorem. Given the random variable x has a distribution and it doesn't specify what kind. So this is what's quite, powerful about the central limit theorem is that it basically applies to anything. Given a random variable with some kind of distribution, could be normal, could be something else, with a mean, and I was being kind of lazy here instead of typing it because I have to go to this whole separate website to get this special math formatting stuff. I just left a space and I was planning to write it in. So with a mean of mu and a standard deviation of sigma, maybe that was a mistake, writing in sigma there. So, which again, basically applies to anything. And two, that simple random samples, all of size n, are selected from the population. So just as long as you're picking simple random samples and they're all the same size, which we're giving the label of n, but whatever size you pick, then what is true is the distribution of sample means. Now this is where things get a little bit tricky to follow because we have our original distribution of data values, which could be normal or not normal. We don't know. It's not required. It just has to have some kind of distribution. That's the original data set. But now we're looking at the distribution of the sample means of samples of size n from the original data set. So we're not looking at the original numbers anymore. We're looking at sample means from samples that were drawn from the original numbers. And we're thinking of the sample means as a distribution or a collection of data values. The distribution of those sample means of samples of size n will, as the sample size increases, approach a normal distribution. So the bigger the sample size you have, the more the sample means will resemble a normal distribution. The mean of the sample means, so we're looking at the mean of our new set of values, which are the sample means of samples of size n. The mean of those sample means will actually, of the samples means, I'm sorry, I just caught that. There's an extra S there, it's not supposed to be there. The mean of the sample means is actually equal to the mean of the original set of numbers, right? So if you consider the notation here, this is the mean of the sample means, right? X bar is a sample mean, so we're looking at the mean of the sample means, and it equals the mean of the original population of data values, right? So the mean actually won't change. The mean of your sample means will be the same as the mean of your original set of numbers, according to the central limit theorem. The standard deviation of your sample means, so sigma with the subscript of x bar, that's the standard deviation, the population standard deviation of our sample means. And we're using population notation here because we are talking about all possible, the sample means of all possible samples of size n. That's the collection of numbers we're looking at. And because it's all possible samples of size n, it's a population, right? And so we're talking about the mean of the sample means of all possible samples of size n. That equals the mean of the original population of numbers. The standard deviation of all sample means, I always struggle with where to put the word all. So let's try that again. The standard deviation of the sample means of all possible samples of size n will equal the original standard deviation of the original set of numbers. Again, I'm having trouble where to put the original at. So it will equal the standard deviation of the original set of numbers divided by the square root of n, where n is the sample size that we've selected. All right, so we are talking about two layers here. We have our original layer for our original set of data, and then we have this new layer, which is composed of the sample means of all possible samples of size n from the original set of numbers. And that's going to give us a new set of numbers to analyze. And that new set of numbers will approach a normal distribution as the sample size increases, even if the original distribution doesn't have a normal distribution, right? The original data set may not have a normal distribution, but its sample means will take on a normal distribution as the sample size increases. And it doesn't take a very big sample size to get close enough to being a normal distribution. So we'll talk about that. I don't know what screen it's on. Let's see. All right, here it is here. For samples of size n larger than 30, the distribution of the sample means can be approximated reasonably well by a normal distribution. So that's all it takes, is a sample size that's at least 30 or more than 30, right? So at least 30 means 30 or more. So I kind of said that funny, but that's all it takes. So if you can get at least a sample size of 30, then the distribution of the sample means will approximate a normal distribution well enough that you can use normal CDF and inverse norm to get results. Right, so 30 or more. Right? And again, the larger the sample size is, the better it does. How do I want to say this? The closer of an approximation you get to a normal distribution. So 30 is just kind of the minimum threshold. It's not the best, but it's good enough to be represented by a normal distribution. But if you have like a sample size of 50, 60, 70, the larger your sample size is, the closer of an approximation you get to a normal distribution for your sample means, right? If the original population had a normal distribution to begin with, then for any sample size n, the sample means will be normally distributed, even if n is less than 30. So if you know your original set of numbers had a normal distribution, then it doesn't matter what the sample size is. The distribution of the sample means will also exhibit a normal distribution. Not just approximately. I mean, it will be a normal distribution. But if your original data set, it's unknown what type of distribution you had, then you're going to want at least a sample size of 30, if not more, in order to ensure that the sample means will approximate a normal distribution. So that's kind of the rule of thumb. If you know your original data set had a normal distribution to begin with, you don't have to really worry about sample size. Any sample size works. If you don't know the distribution of your original data set, then your sample size needs to be 30 or more in order for the central limit theorem to apply, and in order for us to approximate the distribution of the sample means with a normal distribution. All right. Okay. So that's the rule of thumb. And you will be kind of quizzed on that. On some problems, they're going to ask you, like, what was this okay to do? And you might say no, because the sample size was not at least 30. Or it might say the sample size here was less than 30. Why was that okay? And you would say, well, because the original population had a normal distribution to begin with, so it was okay for the sample size to be less than 30. Central limit theorem still applies. All right, so I want to go back to just illustrate how the central limit theorem works, and that it does work, to kind of, how do I want to say this, to confirm that the central limit theorem does a good job of giving you results. I hope I'm saying that right. So I want to go back to the Animal Crossing critic review scores. All right, so I just want to demonstrate the concepts of the central limit theorem and just kind of do a little bit of an experiment to confirm that the results you get from the central limit theorem are valid. All right, so we haven't looked at this data set in a while. I used this data set in like chapter 2, chapter 3. Thought I'd bring it back for this exercise. There's 107 data values here. Now, we were treating this data set as a sample in chapter 2 and chapter 3, but for this particular exercise, I want to treat this as if it's a population. So let's assume that these critic review scores are from all possible critics of Animal Crossing. And so we have every review score from every critic on Animal Crossing. So it's a population, right? And we're going to take, well, I guess let's talk about this. So, and I don't want to go through this calculation on the video. I just pulled it from our previous work. We calculated the mean of this data set. The mean was 90.6. And the standard deviation was 6.09 if you round it to 2 decimal places. And this would be 90.64 if we round that to 2 decimal places. Now remember, for the standard deviation, when you treat it like a sample, you get a different answer than when you treat it like a population. So I'm trying to remember, I got these notes ready a couple weeks ago. I think I redid the calculation so that this would be for a population. And this might not match what we got in the video previously. It might be a little bit different. But that's because earlier we were treating it as a sample, and the standard deviation of a sample, the formula is slightly different than it is for a population. All right, so those are the numbers for that data set. So in order to test the central limit theorem, what I did is I took the entire data set and I put it in a list on this website called random.org. And this is a really interesting website. It does various different things involving randomization. And a lot of its functions are free as long as you don't use it too often. You know, if you run a company and you want to do a lot of random number stuff, you have to like pay money for their services. But just as a single user, just kind of studying statistics, you shouldn't have to pay anything for the stuff that it does. So what I did is I took all the critical, I'm having trouble talking today. This is my third video of the day, which is more than I normally do. And it's like starting to wear me down. So I took the data values from the Animal Crossing critic review scores, all 107, and I put them in this list here, in this box, one on each line. And what the function I'm using here is to take a list of numbers and randomly pick a certain number out of that list. And so I gave it all 107 critic review scores, and then I told it to pick 30 of them at random. All right, so let's see if I have that on the next screen. All right, so here's an example of a result that I got. There were 107 items in your list. That's our 107 critic review scores. I guess I didn't tell it to pick 30. I just said randomize the order. So it took the 107 data values in the data set and changed the order randomly. And then for my sample, I just took the first 30. So there are 30, the first 30 numbers are 30 random numbers from the data set. And that's how I got my sample size of 30. It was done in a random way, so the central limit theorem should apply. Right, so I took 107 data values, randomized the order, took the top 30 numbers in the randomized list as my sample. I did that multiple times. Right? I think I did it 15 times. It's a little bit off the chart there, but there's 14. I have one more on my screen that you may not be able to see. So I did this 15 times. So I got 15 different samples of size 30. Right? So here's my first sample. There's 30. These are the first 30 numbers in the randomized list the first time I ran it. Here's the first 30 numbers in the randomized list the second time I ran it. Here's the first 30 numbers the third time I ran it. So I'm getting 30 random numbers from that data set, and I did this multiple times, did it 15 times. So what I did with my samples, right? So these are samples of size 30 from that population of 107 data values, is I took the mean of each one, right? So here's the mean for the first sample, 91. Here's the mean for the second sample, 93.03. Here's the mean for the third sample. So I'm collecting a set of sample means from samples of size 30 from the Animal Crossing review scores. So again, layer upon layer upon layer of numbers, right? And what I did is I took these 15 sample means and I took the average of the 15, right? So the mean of my sample means, now this is not a full testing of the central limit theorem, because the mean of the sample means for the central limit theorem would involve every possible sample of size 30 from that population. And there would be an astronomical number of possible samples. I wouldn't be able to actually find all of them. Again, if you go by the counting that we talked about, and I can't remember which section it was, but where you kind of do like this, there's 107 possible values for the first number, 106 for the second one, 105, and you'd have to multiply all those together, all the way like 30 of these, 107, 106, 105, get 30 of those numbers and multiply them together. It's going to be a huge number, and that's how many different possible samples I could get. I'm not going to be able to find them all and then find the mean of each one. So I just did 15 just as a test case, and I took the average of these 15 sample means, and I got 90.87, which is pretty close to the mean of the original population. So that seems to confirm that the central limit theorem does a pretty good job of what it purports to do, right? The central limit theorem says, I said that funny, the central limit theorem says that the mean of the sample means should exactly equal the mean of the population. And it would if I went and found every possible sample of size 30, calculated the mean, averaged them up. I would get 90.6, right? And so, but even just doing 15, I get pretty close, right? I get 90.87. That's pretty close to 90.6. So it does appear that the mean of the sample means should be equal to the mean of the original population, because even in this limited case, it's pretty close to that value. And the central limit theorem says that the standard deviation of all these sample means should equal, so what it should end up being is the original standard deviation divided by the square root of the sample size. Now my original standard deviation was I can't remember what the decimal places were. Let's go back to that. 6.09 if I go 2 decimal places. 6.09 divided by the square root of our sample size was 30. Now again, this might not exactly equal this, because this is what it would be if we found every possible sample of size 30. I only did 15 samples of size 30. There's many, many, many more possible ones. And if I took all of those and found the standard deviation for all of them, I would get exactly this thing I'm about to calculate now. But what I'm hoping is the case is that this will be pretty close to what I got just for the 15 that I found. Again, to just confirm that the central limit theorem does seem to be describing something that's true, right? So we have 6.09 divided by the square root, and I haven't done this ahead of time. This is risky. I'm recording myself live. I'm not live, I guess, but I'm not going to re-record this. And I could be completely wrong, possibly, right? I'm taking a chance here, but when I saw the result, I was like, that looks like about what it should be. But I haven't really tested it. I didn't actually confirm it. So in my calculator, I'm doing 6.09 divided by the square root of 30. And that gives me, that's a little off. It's a little off. 1.111, and it's several ones there. So, but pretty close to the 0.07, right? I said 0.07. I don't know why I said that. 0.7, right? It's within 0.5 of the value that it would equal if we had every possible sample of size 30. So for the 15 sample means that I found, the standard deviation was this. But if I found all samples of size 30 from the population, this would be the standard deviation that I should find. And they're in rough agreement. Not maybe as well as the means were, but close enough, right? So that's, and plus I wanted to go through this exercise so you can just see the layers of the numbers that we're dealing with, right? We have our original data set, which were the Animal Crossing review scores. From that, we're taking samples of size 30. So we're getting several samples of size 30. And from those samples, we're calculating the sample mean. And then we're looking at the mean of those sample means, right? That's the level of processing that we're doing with this data set, right? And that's what the central limit theorem is looking at. It's not looking at, so when you're using the central limit theorem, you're not looking at the probabilities for the original data set, like the original Animal Crossing review scores. You're looking at the probabilities for sample means of samples of size 30. And our probability would be that the sample mean would equal 90.5 or be greater than 90.5 or something like that. Or the probability that a sample mean would be less than 90. That's using the central limit theorem, because now you're looking at the distribution of the sample means, not the distribution of the original set of numbers. And that's the thing you have to be careful about. And I think when you see these examples, there's a really easy way to tell when the central limit theorem should be applied. And that is if they're asking you for a probability involving more than one thing, more than one person, more than one item, or whatever it is that the population, whatever the population happens to be, right? So assume the population of weights of men is normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. Right, that's the original data set. We're assuming has a mean of 172 and a standard deviation of 29. Part A asks us to find the probability that if an individual man is randomly selected, his weight is greater than 175 pounds. Contrast that with part B, where it says find the probability that 20 randomly selected men will have a mean weight that is greater than 175 pounds. Right? So if you kind of gloss over the details of those two questions, they almost look like they're the same question. They're both asking for the probability that a weight is greater than 175 pounds. The glaring difference there is that part A is about the probability of an individual's weight being greater than 175, whereas part B is asking for the probability that 20 people have an average weight that's greater than 175. So the thing that really sticks out that distinguishes these two questions is part A is about one person, part B is about 20 people together having an average weight being greater than 175. So for part A, you do not use the central limit theorem because you're asking for a probability regarding the original set of data. And so you just calculate it the same way we did in the previous video in section 6.2, which is finding the probability using normal CDF, and nothing changes. Like part A is just going to be, basically part A is a review of what we did in 6.2. Finding a probability from the normal distribution using normal CDF, right? So for part A, I guess I'll do that up here. We want to find, so here's the normal distribution, poorly drawn, but the mean is at 172. And I want to find the probability that if I randomly select a man, that their weight will be greater than 175. I probably really should just redraw this. I did a bad job. Okay, let's just redraw that whole thing. Okay, so here's the normal distribution. Let's give a little space there for that. Okay, so this is 172. That's the mean. 175 will be to the right of that. But I wouldn't really think of it as being too far into the right tail. It's just a little bit to the right of, in fact, really, this is probably too much space between these two numbers, but I just want to make it easy to read. And we want the probability that if we randomly select a man, that their weight would be greater than 175. So I want to find the probability that X would be greater than 175. Now, if you had to, again, use your intuition, I think it's kind of a fun exercise whenever you're doing a probability. Guess what you think the answer might be first, and then see what it actually is from the calculator, just to see if you have a pretty good sense of what it should be. How good is your intuition on these probabilities? Now, if you think about the standard deviation, it's 29 pounds. This is well within one standard deviation, right? This is only 3 pounds away. One standard deviation away would be 29 pounds away, which is going to be closer to like 200 pounds. And even just going one standard deviation away, you expect 68% of your data values to be within one standard deviation. I think that's the number. I should know that, but it's I think the rule of thumb is like 68%, 95%, and then 99% or something like that for 1, 2, and 3 standard deviations. So this is so close to the mean that I'm guessing this is going to be like 48%. That'd be my guess. So let's find out if I'm right. So we're going to do normal CDF. Because again, just like we talked about in 6.2, we have the data values. We're looking for this area. That's what normal CDF is for. And then to input the, how do you say? I don't even know what I want to say next. The input for normal CDF is the lower bound, which is 175. Right? That's the lower bound for this area that's shaded in. Comma, the upper bound, which is it goes to the right forever. And again, I talked about this in 6.1 in the video for 6.1. Yes, there is an actual upper limit to how much somebody can weigh, right? So, somebody can't weigh 5,000 pounds, but the model that we're using to model men's weights goes forever to the right. It goes to infinity, even though at some point, biologically speaking, those numbers become impossible. In order for the model to work, we have to let the area go to infinity, forever to the right. So there's always some area, even at 5,000 pounds, there's going to be some area there, and therefore some kind of probability associated with that, even though we know the probability of somebody weighing more than 5,000 pounds would be 0, right? That's just not possible. But for the purposes of using normal CDF, we have to go all the way to the right forever, which is infinity. And remember, I guess I've been using infinity here. And some calculators will let you put infinity, but I've been using 9999999 in my calculator. I don't think my calculator would let me put infinity there, but even if it did, I don't know where infinity is on my calculator. I have to go search for it. It's just easier to do 99999, even if I could use infinity. All right. And then we want the mean, which is 172, and then the standard deviation, which is 29. Right. So we end up getting normal CDF, 175, comma, I'm going to do 99999, but you could also maybe try infinity. The mean's 172, the standard deviation is 29, and I get 46%. So I said 48. I was a little bit off on that too. And the more you try that, the more you try to guess the answer and then see what it actually is, the better you'll probably get at building up the intuition of what to expect. So it's actually 4588, which is about 46%. All right. So that's the answer for part A, that if we randomly select one person from the population, that their weight would be greater than 175 is about 45%, 46%. That's a different question than part B, which is asking, find the probability that 20 randomly selected men will have a mean weight that is greater than 175. So if I was going to write that out, I'm trying to find the probability that the mean, not just X, but the mean, so X bar, is greater than 175. So that's what would change here. Contrast that with how I wrote the probability up here, right? I just use X because there we're talking about an individual. And so X is representing the weights of individuals. It's the random variable. But for part B, I'm not finding the probability of an individual using that random variable. I'm trying to find the probability of a mean of that random variable of samples of size 20, right? The sample size is 20 here, which again is it's not bigger than 30, but that's okay because the original population had a normal distribution to begin with, so the sample size doesn't need to be bigger than 30. Central limit theorem still works either way. Right. So because we're trying to find a probability and it's involving more than one person, we need to use the central limit theorem, which is often abbreviated CLT. Now, what the central limit theorem tells us is that the distribution of the sample means will also be a normal distribution. So to calculate this probability, I'm going to draw another normal distribution. But it's not the same as this normal distribution up here. This normal distribution is for the weights, it's the distribution of the weights of men. This normal distribution down here, I guess I could just leave it there, is the distribution of the sample means of all possible samples of size 20 from the population of the weights of men, right? So this, even though the pictures are going to look the same, this distribution here, the numbers I'm using to form this distribution are different than the numbers that are forming this distribution. Part A, the numbers forming that distribution are the weights of men. Part B, the numbers forming that distribution are the sample means of samples of size 20 that are taken from the weights of men. So you see the difference. These are directly the weights of individuals. These are averages. The set of numbers we're working with here are the averages of 20 randomly selected men. I don't know if I'm saying that in the best way, but so the set of numbers here are the sample means of all samples of size 20. I feel like I'm just repeating myself again. I'm trying to think, as a teacher, you want to try to say things in maybe slightly different ways because like what clicks with one person might not click with another person. So you say it a little bit differently. But sometimes, I feel like there's just one way to say it. There's just one best way to say it. And maybe if I say it enough times, it'll click with everybody. But anyways, we're dealing with sample means down here. That's what this distribution is representing, is sample means, not directly the weights of individuals, but the average weight of 20 individuals is what this data set is representing. All right. So our picture is going to look roughly the same as, in fact, it's going to look exactly the same because the mean of these sample means, remember the central limit theorem tells us, the mean of the sample means just equals the mean of the original population, which is 172, right? So 172 will still be in the middle. What changes is the standard deviation. So really, if I wanted to draw these realistically so that when you compare them, the comparison's a little better, is there should be less variation here because the standard deviation changes to be smaller. And so it should be a more narrow bell shape. This will be more broad because there's more variation in the individual weights of men. There's going to be less variation in the average weights of 20 men than there is in individual men. I don't know if that makes sense or not. But if you're taking 20 men at random and averaging them, the average weight of 20 people is going to tend back towards the middle, towards the average of individuals, right? And so you might have a couple of heavy people, you might have a couple of light people, but when you average it all out, these 20 people, the average is most likely going to be pretty close to 172, and it's not going to go far away from that. So there's less variation in the sample means because when you average things, the average tends to go back to the middle. So most of your sample means are going to have samples that are closer to the middle and less on the fringes. Whereas individuals, there's a lot of variation, right? You have heavy people, you have light people, you're going to have a lot more variation in the individual weights. And so really this should be a more narrow bell shape. But for the purposes of just sketching it out, just to have a sense of what's going on, you don't have to think about it as much as I'm talking about it. So just draw another normal distribution picture, mark the 175 again, and shade in the area. So we're looking for this area here. Again, we have the data values. We're trying to find the area, so we will use normal CDF again. So far, part B is looking exactly the same as part A. The lower bound is still 175. The upper bound is still infinity, which I'll put 99999 for that. The mean is still 172, so not even that changes. But what does change is the standard deviation. It will not just be 29 this time. We have to use the central limit theorem, which tells us that for the sample means, the standard deviation changes to 29, the original standard deviation, divided by the square root of the sample size, which is 20. And that'll be my new standard deviation, right? And so here, even though it didn't change, I just want to point out what I'm inputting here is the mean of the sample means, which just so happens to be the mean of the original population. Here, I'm putting the standard deviation of the sample means, but that equals the original standard deviation divided by the square root of n. And that's what I'm putting here. Right, so we're shifting the mean and the standard deviation according to the central limit theorem from the mean and standard deviation of the original data set to the mean and standard deviation of the sample means of all possible samples of size 20. Right, and it turns out the mean will stay the mean. It'll stay 172, but it's the standard deviation that will have to be adjusted. So if you really want me to boil it all down, because I know I've done a lot of talking and we've barely just done this one example so far, but for this, this is as simple as I could make it, I think. If your probability involves more than one person, you want to use the central limit theorem, and that means changing the standard deviation. That's the only thing that really ends up changing. From the original standard deviation to the original standard deviation divided by the square root of n. That's the one change you have to make. Everything else is going to stay the same in this problem as it was in part A. All right. Now, you might say, well, what does that equal to? You don't actually have to compute that. You can just type what I have on the screen into your calculator, and it handles that kind of number just fine. So I'm going to do normal CDF. We're going to have 175, comma, 9999999, comma, 172 for the new mean, which just happens to equal the old mean, and then 29 divided by the square root of 20 for the new standard deviation. And then you have to close the parentheses on the square root, at least in my calculator you do, and then I'm closing the parentheses on the normal CDF. And I hit enter, and this time the probability is 0.321. It's smaller. Right? It's less likely that the average weight of 20 men is going to shift as far to the right than an individual person's weight shifting that far to the right. Right? So the chance of one person weighing more than 175, which is over the average, is much higher than the chance that 20 randomly selected men would have an average weight that's that much higher than the mean, the average, right? So to have 20 people with an average weight exceeding 175, it's not rare. I mean, it's 32% of the time that will happen, but it does happen less frequently than an individual's weight being more than 175. Right. So going further out into these extremes to the left tail or the right tail, when you're dealing with sample means, the probabilities drop really fast. So if we went out to like 180, this might still be something like 40%. It'll be pretty high, but here I bet it would drop down to like 10% or something like that. So even just going a little bit further, like 180, 185, because to have the average shift that far for 20 men, that's hard to do because you'd have to have a lot of men over the average weight to shift the average of those 20 people that far to the right. Whereas an individual, it's not that hard for that to happen, right? It's not that hard to find one person whose weight has shifted that far to the right. But to have 20 people with their average shifting that far to the right is more difficult to accomplish. So anyways, just trying to explain conceptually what's going on, but really it just comes down to most of these problems will have part A, part B. Part A is the individual. You don't make any changes. You just do the normal CDF with, the mean and the standard deviation that's given. Part B, you change the standard deviation because of the central limit theorem, and everything else will stay the same. And you'll get two different probabilities. And generally, the probability for part B will be less than the probability for part A. All right, so let's try that out again with this problem, and then maybe I'll have you guys try an example. And we're pretty close to being done. If I didn't talk so much, I probably could have done this in like 20 minutes because it's just more normal CDF stuff, which we did in 6.1 and 6.2 with just an adjustment that has to be made. But the important part isn't so much the calculation itself, because especially with the calculator, it's not that hard to do. It's the same thing we were already doing. We just have to make a change to the standard deviation. But the important thing is the concepts behind it. That's really what I'm hoping you'll understand from this. Like, not just how to mechanically get the right answer, but just understanding what's going on behind the scenes, right? Okay, what's the math that's happening that leads us to have to make that change? That's what I want you to understand. Assume that SAT scores are normally distributed with a mean of 1,518 and a standard deviation of 325. If one SAT score is randomly selected, find the probability that it is greater than 1,600. So again, this is an individual, it's 1. So we don't need to use the central limit theorem here. We're calculating a probability on the original set of data. And the original set of data has a mean of 1,518 and a standard deviation of 325. And so we will just do normal CDF. There's our mean, there's our standard deviation. No adjustments have to be made because we're talking about the probability involving an individual from that original population, right? So for part A, you draw a picture. The mean is 1518. We're looking at the probability of somebody having an SAT score greater than 1600, which is going to be to the right of 1600. So we want the area to the right of 1600. To find that area, we will use normal CDF. And the lower bound there is 1600. This problem's actually a little bit too similar to the last one because it's lower bound, we have a number for that. It's a different number, but it's a number. The upper bound is infinity, just like the last example. The mean this time is 1518, so we do have to make that change. And the standard deviation is 325. And so we'll get this answer. So normal, oops, did the wrong thing here. Normal CDF. 1600 is my lower bound. Infinity is my upper bound, but I'm just going to do 99999. 1518 is the mean, and 325 is standard deviation. And I get a probability of about 40%, 0.4004, if I go 4 decimal places. All right, So the average being 1518, it's not too far of a stretch to, find somebody that got an SAT score of 1600. It's within a standard deviation. So again, it hasn't deviated that far away from the mean. So it's pretty common. 40% chance that if you pick somebody at random, you pick somebody that had an SAT score greater than 1600. Now, part B is asking the probability that if we have 64 people that took the SAT that we've randomly selected, what's the probability that their mean SAT score is greater than 1600? So not only is one difference that's easy to spot individual versus group, right? But also, if it's asking for the probability of a mean, you have to use the central limit theorem to calculate that probability. Because now we're not looking at the original data set anymore. We're looking at the data set of means. And the central limit theorem tells you how to adjust, how to convert your mean and standard deviation from the original data set so that it gives you the mean and standard deviation of your new data set, which is the means of the original data set, right? From samples of size 64 in this case. Right? So the central limit theorem tells us how to convert our original set of data into the set of data involving the sample means, which is what part B is asking us to find a probability about. Right? So we're trying to find the probability, and I didn't write this here, but this was the probability that X is greater than 1600. X being an individual having an SAT score greater than 1600. In part B, we're trying to find the probability that a mean SAT score out of 64 people is greater than 1600. So to move the needle past 1600 with a group of 64 test takers is going to be more difficult to do because, 1600's quite, it's a little ways above the average. And to get that many SAT score, I wanted to say something different there, to get that many SAT takers with scores that are high enough to bump the average to the right, it's going to be more difficult to do than just finding one person that has an SAT score that far to the right. So the probability should be smaller. Now, I'm not sure how much smaller. The last one, I'll admit, I didn't say what my guess was, but I was thinking it was going to be less than 32%. I was thinking something like 10% or 15%. So I was off. My intuition was off on that one. So if I had to guess on this one, I'm thinking the probability that the mean would be greater than 1600. I don't know. Maybe this one's going to be like 10 or 15%. So let's find out if my intuition's right. So to calculate this, we're going to do, it's the same picture. I could redraw it, but it's the same picture. The mean doesn't change, right? This will stay the mean of my sample mean. So the center will still be 1518. And I'm still looking at 1600, and I want to find the means that are greater than 1600, which will be to the right. So I want the area to the right. So really, if I was going to draw a picture for this, it's going to look exactly like this. And I'm going to do normal CDF. The lower bound is still 1600 because they stuck with that same number in part B. The upper bound's infinity. The mean is still 1518. That's what the central limit theorem tells us, right? So I'm not just putting 1518 there because that's what I had up here. I'm putting it here because the central limit theorem tells me that the mean will stay the same. This is the mean of my sample means, and it should equal the mean of my original population. That's why I'm putting the same number there. But the standard deviation will not stay the same, right? This is the standard deviation of my original population. The standard deviation of the sample means is going to be 325 divided by the square root of the sample size, which in this problem is 64. Bigger sample, which makes it even more challenging to move the needle that far to the right. If it was maybe 20 people, maybe that wouldn't be as bad. You just got to get a couple of high SAT scores in there and you're probably in good shape. But 64, you get a couple of higher SAT scores. That might not be enough if everybody else is kind of more average, right? So we have to get several exceptional SAT scores in that group in order to get the average to go up to 1600 or more, right? So let's find out what that probability is. Again, I'm hoping the concept there makes sense to you, why the probability is going to be smaller here. So we have 1600, 9999999 for infinity, 1518 for the mean again. But this time we'll have, again, you don't have to calculate it unless you want to. You can just type in 325 divided by the square root of 64. Close the parentheses on the square root, and then close the parentheses on the normal CDF. And I'm getting, oh, wow. My intuition, okay, so on the last problem, I underestimated the probability. I thought it would be lower than 32% or whatever. I can't remember what the answer was, but I thought it was going to be lower. This one, I thought, oh, maybe it'll be about 10 or 15%, and I overestimated it. It's much lower than I would have expected. So again, and this is actually kind of, it's interesting because like, this is why statistics and probability is so valuable to study, because intuitively people are pretty bad at statistics and probability. Like we just don't have, it's just not a natural ability for most people to have a good sense of probabilities and, statistics. And so it's good to have these tools to correct our bad intuitions, right? This is like lower than I thought it would be. 0.0218 if you round to 4 decimal places. So less than a 2% chance, right? That's a pretty dramatic difference, right? The chance of one person having an SAT score of 1600, not that hard to find, right? 40% chance of that happening. But the chance that we would get 64 randomly selected people to have an average that exceeds 1600 is only a 2% chance, right? Because we'd have to get a lot of exceptional SAT scores in that group to move the needle that far, right? It's the best way I can think to describe it. The more people you throw into that sample, the more stuck it becomes at the middle, because the most likely numbers you get in there are going to be ones closer to the average. And so to get, again, to get an average of 1600, you're going to have some exceptional SAT scores in there to balance out the average ones and the low ones, right? Because remember, for all the SAT scores in the right tail, there's some over here in the left tail that are, just as exceptional, but in a bad way, and those are going to kind of cancel each other out. So the average really comes back to the center, right? So you'd have to not only have exceptional SAT scores to balance out the bad ones, but you're going to have more exceptional ones that are good than exceptional ones that are bad if you want the average to get bumped up that far to the right. Okay. So I think we got a couple more examples, a couple more scenarios to look at. Now this one's SAT scores again. It's really a repeat of the same problem, but just, different bounds that we're looking at here. In fact, the sample size is exactly the same as 64 again. So let's see. Oh, that's weird. I must have made a mistake because part C doesn't make sense. Why can the CLT be used in part B even though the sample size does not exceed 30? It does exceed 30. So I must have did a copy and paste job and then did not change that number. So let's change this number in a way that it makes sense with part C. So let's change this to 16. I think they pick a number here that it's a nice square rootable number. So let's go with 16 there for that. So what I want you to do, this is SAT scores again. The mean is 1518, standard deviation is 325. Pause the video. I'm going to pause the recording. I'll work out the solutions to parts A and B off camera. And I want you to pause the video and work on those problems as well to see what you come up with. And then resume the video to see if the answers you get match the answers that I got. And then we'll talk about part C together. So go ahead and pause the video. And once you have some answers, resume and see if you came up with the right answer. Okay, so we got some pretty interesting results here. For part A, the probability you should have found is 0.0483. That's the probability if we randomly select one SAT taker that their score was between 1440 and 1480. What's interesting here is that if we look at the part B, the average, the probability is higher. So I mentioned earlier in the video that normally part A, you get one probability, and part B, you get a smaller probability. But that's because normally we're looking at like the extreme, like going from one value all the way to the right or all the way to the left. This one, we're kind of looking at a narrow band. And to have an individual fall in that narrow band is unlikely because it's pretty narrow. But to have the average fall in that narrow band when it's so close to the mean is actually more likely than an individual falling into that narrow band. So again, my intuition, I wouldn't have maybe have expected that, but that is what the numbers bear out. So the probability that a group of 16 people would have an average score between 1440 and 1480 is about 15%. 0.1515 is what you should have got for part B. Now, why can the central limit theorem be used in part B, even though the sample size does not exceed 30? Because the original data set had a normal distribution to begin with. And if that's the case, then sample size doesn't matter for central limit theorem. It automatically applies regardless of the sample size. So that's why it is okay. But if the original population does not have a normal distribution, or it's unknown what the distribution is, then the sample size needs to be 30 or greater. And if it's not, that would be an issue. All right. We have one more scenario to look at here, and there's parts A, B, and C on this one too, but they're on separate screens. So there's really basically one more problem, and then we'll be done. The Boeing 757-200ER airliner carries 200 passengers and has doors with a height of 72 inches. Heights of men are normally distributed with a mean of 69.0 inches and a standard deviation of 2.8 inches. If a male passenger is randomly selected, find the probability that he can fit through the doorway without bending. All right. So again, this is an individual. And for an individual, a male passenger, we don't need to use the central limit theorem. Right? No adjustments have to be made. Right? We have the mean, which is 69.0. We have the standard deviation, which is 2.8. And that's what we use in our normal CDF. So you can draw a picture if you want. The mean will be in the middle, so 69. We're looking at being able to fit without bending. And so the height of the door is 72 inches. That's going to be to the right of 69, so it'll be over here. But in order to fit under that doorway without having to bend, your height will have to be smaller than 72 inches, right? Not great. If you're taller than 72 inches, you're going to have to bend. You're going to have to duck under it. But if your height's less than 72 inches, you can pass through without having to bend. And that's what it's asking. So this is an interesting question because it's not literal. It's not saying find the probability that the height's less than 72 inches. It's just you have to infer that from the description. What's the probability that he can fit through the doorway without bending? You have to realize, well, in order to fit without bending, my height would have to be less than the height of the doorway. The height of the doorway is 72 inches. As long as my height's less than that, I won't have to bend when I pass through it, right? And so we're looking for the probability that if we randomly select a male passenger, that their height is less than 72 inches. The heights that are less than 72 inches are to the left of 72, so we want the area under the curve to the left of 72. So this area here that I'm shading in. Right, that's the area we want. That'll be the probability that a randomly selected male passenger has a height less than 72. And to find that probability, we're going to use normal CDF, just like we've done on every problem in this section. This time, the lower bound is negative infinity. So finally, we have an example where the area is going to the left instead of going to the right. And so the lower bound, since it goes to the left forever, is negative infinity. Again, even though heights stop at 0, or even really before that, right? Because, a person's height, even when you're born with like 24 inches, somewhere in that neighborhood, 2 feet. You're 2 feet tall when you're born. And so, a height of 1 foot may not be a possible height for humans, right? And that might be where the heights literally stop. But the mathematical model here requires that the normal distribution goes forever to the left, forever to the right, and that it never reaches the x-axis. That's what we need in order for the numbers to work. And so even though heights might stop at 1 foot or 2 feet, we're going to let the lower bound be negative infinity, even though that's going to have a lot of heights that aren't even possible. All right. The upper bound here is going to be 72. The mean, 69. The standard deviation is 2.8. Sorry, the decimal place looked kind of funny there. And that's what we type into our calculator to get the probability. And we did not use the central limit theorem. I didn't have to make any adjustments to any of these numbers because I'm finding the probability from the original data set, from the original heights of men. All right. So normal CDF, negative 9999999, comma 72, comma 69, comma 2.8. And I'm going to get 0.8580. So that's the probability that a randomly selected male passenger will have a height less than 72 inches and will therefore be able to fit through the doorway without having to bend. All right, part B, same question, except we're looking at a group of male passengers instead of just one. So assuming that half of the flight is composed of male passengers and half composed of female passengers, find the probability that the mean height of the 100 men on the flight is less than 72. Right, so now we're talking about a group, we're talking about a mean, so we have to use the central limit theorem to calculate this probability. The picture still looks the same because the central limit theorem tells me that the mean of the sample means, which is now the set of numbers I'm calculating the probability from. I'm not calculating the probability on the original set of heights that we have. I'm calculating the probability on the sample means of all samples of size 100 from the heights of men. Right? The central limit theorem tells me, however, that the mean of all those sample means that I'm now working with will equal the mean of the original population that those samples were drawn from, which is 69.0. And then the standard deviation of all those sample means will equal the original standard deviation, but divided by the square root of n. In this case, n being 100. Right? So we're going to get the original standard deviation, which is 2.8, divided by the square root of 100. And again, you can, this is actually really easy to calculate even without a calculator. Square root of 100 is 10. 2.8 divided by 10 is going to be 0.28. So you could use either one of these. We've been using this the entire time, so I'm just going to stick with that. And so the picture, I think I referred to drawing earlier. Oh, that was like the worst one I've drawn so far today. Let's try that. Okay. The mean's in the middle, 69, 72. We want to find the probability that the average height is less than 72. But again, this drawing, while it looks the same, is in reference to sample means of all samples of size 100. Whereas my original drawing for part A is just the heights of men, right? This is all the heights of all the men in the population, right? And that's represented with the letter X. This is the sample means of all possible samples of size 100 drawn from the heights of men. That was the original population. Okay, so I've repeated it probably more times than I should have in this video. Hopefully by now it's making sense. All right, so we want to find this area. We'll do that by finding the probability that the mean, so x bar is less than 72. That'll be that area, which we will find by doing normal CDF again. The lower bound is negative infinity. The upper bound is 72 again. The mean of the sample means is still 69, but the mean of the standard deviation of the sample means will be the original standard deviation of 2.8 divided by the square root of the sample size, which is 100. All right, so we'll plug that into our calculator and we will get the result. And again, I want to test my intuition on this thing. I'm guessing we'll get a higher probability because, again, we are, the average height of 100 men should be close to the center, which is close to the average height of men in general. So I would expect the average for a group of 100 randomly selected men to be close to 69 inches, right? Since that's the mean of the original population. So the average, especially with 100, even if you have a few tall people in the group, you're going to have a few short people that kind of balance that out. And the average is just going to come right back to the middle, right? In order to get the average to exceed 72, you're going to have quite a few tall men, more than you have short men. So you're going to have average height men in the group anyways, but you would need more tall people than you do short people to skew your average more to the right. So if you want to move the needle more to the right, you're going to have more tall people than short people in that group. And if you're randomly selecting people, you don't get to choose that, right? It's just random. You just have to hope that randomly you end up with more tall people than short people. And that's just not likely to happen very often. So I would imagine that this area to the right is pretty small. Having the average height of 100 men be that much more than 72 is probably very unlikely to happen. So I would imagine that this is small, and then so the area to the left would be 1 minus that small number. So I'm actually feeling like, now that I really analyze it, I'm thinking 99%. I think the probability that the average is less than 72 is going to be like 99%. So let's see if I'm right. Okay, so negative 99999 for the lower bound, 72 for the upper bound. The mean is 69. The standard deviation is 2.8 divided by the square root of 100. Close the parentheses. And oh, it's even more extreme than that. So when I do this calculation, the answer my calculator gives me is 1. Now we know that means if the probability is 1, that means it's certain to occur. And that really isn't literally the case here. What happened is the actual answer is 0.999999, so many nines that the calculator couldn't hold all of them and was forced to round. So when you get to that last place value and you can't add another 9, you're going to have to round this one. Well, if you round this one, because that's a 9, this rounds up to a 0. That's going to round up to, it has that domino effect, and it ends up just, rounding it up to 1. Right? But really the probability is 0.999999, bunch of nines. Right? So it's not literally certain to occur, but it's practically certain that in a group of 100 randomly selected men, the average height would be less than 72 inches. Right? So for my stat lab, when it asks for this answer, you're going to type in 1, because whatever it wants you to round to, wherever you end up having to round, it's going to be, like I said, there's so many nines, it goes off the charts on the calculator. So Math Excel, I keep saying Math Excel, my stat lab, wherever it might ask you to round wouldn't be that far. And so you're going to have to end up rounding in the same way. Wherever it does ask you to round, there's so many nines there, you're going to round it up, and it's just going to round it up to 1. And so your answer will be 1 in this case for part B. All right. When considering the comfort and safety of passengers, which result is more relevant? The probability from part A or from part B? So in having this business of being an airline, you want your, I don't know, you would think they want their customers to be comfortable, but I don't know, the way they really squeeze everybody in there as close as possible, maybe that's not as much of a factor as we would like. But as a business, it's about individual customer service, right? You want each person to feel comfortable. You don't want the average person you don't want it to be the case that, well, on average, people feel comfortable, or the average person is going to feel comfortable, because not everybody is average, right? So in this case, if they were going for just making sure the door height worked for the average person, they're, excluding tall people, right? They're saying we don't really care about tall people. We just care about average height people being able to fit through our door. And that's really probably not the best approach to take. So in considering the comfort and safety of passengers, maybe I don't know so much about safety, but comfort-wise, you should consider the probability from part A, that you want individuals to feel comfortable, not groups of 100. How do I want to say this? You don't want the average person in a group of 100 to feel comfortable, because not everybody in that group is going to be the average. You want each person to feel comfortable in that group, which means you're more interested in the probability of the individual being able to fit comfortably than you are with the probability that the average person out of that group of 100 is comfortable, right? So, you want good personal customer service. You should be more concerned about individuals being able to fit comfortably through the door, to be able to sit comfortably, things like that. Now, for the safety part of it, I don't know. I mean, planes have certain, dimensional restrictions, right? You might not be able to make a door height that's 80 or 90 inches that would just allow anybody to walk through without having to bend. So there's that aspect to consider as well. So you want to try to, maximize both, right? You want people to be as comfortable as possible, while at the same time you want to be as safe as possible in how you build your airplane. And you want to make as much money as possible, which is why you want to try to cram people into as small of a space as you can without them complaining too much that they refuse to fly, right? So I think they're trying to strike that balance of how can we make the most money and keep people just comfortable enough that they keep flying with us, and that we can fly them safely, right? So all those things have to be considered. Anyways, that concludes the video on section 6.4. I'll see you in the next video for section 7.1.